All right, our second type of special factoring for polynomials is when we factor a perfect square trinomial. So you might be wondering, well, what do I mean by a perfect square trinomial? So here's our definition up on the screen. It's a trinomial whose binomial factors are the same. For example, in blue here, we have a perfect square trinomial, x squared plus 10x plus 25. And what makes it a perfect square trinomial is that the two factors, so when I factor this out, I get x plus 5 times x plus 5. And notice that one binomial is the exact same as the other binomial factor. Another way we could write that, because we are multiplying something by itself, is to just simply say that it's x plus 5 squared, because the little exponent means you're multiplying x plus 5 by itself. And this really only works if you are multiplying the same binomial twice. Here we have our area model to kind of display that. We have x squared plus 10x plus 25, and it's the result of x plus 5 on the top times x plus 5 on the side. So we have x times x times 5 was 5x, 5 times x was another 5x, and then 5 times 5 was 25. So we get our total area, which represents the perfect square trinomial, and then we have the length and the width are each the same, x plus 5. Which is the binomial factors. Okay, so that's what I mean by a perfect square trinomial. It's just a pattern where the length and the width are the same. So really, this area model becomes a square because the sides are the same. So here's more generically how we can look at this, because our pattern comes with just understanding what these two parts to our binomial are, the a and the b. If we multiply it by itself, so a plus b times a plus b, we do this in our area model to show it. I'm going to get a squared in the first box, and then I'm going to get ab in my like terms boxes. So basically, I have two of the ab's, and then I have b squared at the end. So all together, when I multiply a plus b times itself, I get a squared plus 2ab plus b squared. Now you have to watch out, because a lot of students will look at this and say, oh, I see. It's just a times itself, which is a squared. And then it's b times itself, which is b squared. But when students do that, they often forget that, there's that 2ab that goes in the middle. There's that third term, the like terms part of our perfect square trinomial. So we have to keep in mind that a plus b squared is not the same as just a squared plus b squared. There needs to be that third component that gives you the like terms, and the area model gives us a better visual for that. Now the same can be said when it's subtraction. The only thing that's going to change then is that the ABs are both going to be negative, so that is going to make this a minus 2AB. And we'll see that in some examples here. All right, so first one, we're just going to take a look at multiplying the x plus 3 times itself, just to give us a better understanding of how these numbers or how this pattern develops. So we have x plus 3 multiplied by itself, x plus 3. And when we do that, we'll get x squared, we get 3x, we get 3 times x again, and in the last box, we get 3 times 3, which is 9. So basically, we get x squared plus 6x plus 9 as the area of that area model. And in the other example, if we take x minus 7 and square it, that means we take x minus 7 multiplied by x minus 7. It's not the same as just x times x and 7 times 7. That's enough to give us the first box and the last box, but it ignores the fact that there's two other areas that are part of this total area. So we have to multiply negative 7 times x and negative 7 times x again, which will give us that middle term of negative 14x. So x squared minus 14x plus 49. So that's really more like how we would have multiplied polynomials in Unit 8. It's just looking at it that way. But I want to really focus on that relationship and the numbers that we see. We see that the first part of the binomial factor is x, and when we take x times itself, we get the first term in our perfect square trinomial. So that happened in both cases. Okay, like the x times x is x squared. That's this first box. Now, when we take the 3, we get, well, 3 times 3 is 9. So basically, if we take that 3 and square it, that's going to give you this number at the end. Same thing's happening in the other example. We take this 7, or technically negative 7, and we square it. Negative 7 times negative 7 is still positive 49. So in this pattern, any way that you look at it, you're going to end up with a positive number at the end. Okay, whether it's plus 9, plus 49, or plus something else. And it should represent a perfect square because we're multiplying a number times itself to get that number at the end. Now, if we look closer at the relationship between the like terms, for example, we have this 3x and 3x, and that's really just the result of multiplying together the two parts of the binomial. So x times 3 is 3x, and it just so happens that I have two of those. 3x and another 3x gives us 6x. And if we look at how that worked in the other example, number 2, same thing's happening here. X times negative 7, and I know that says x minus 7. I'm just using the relationship between these two. If we were to multiply the two parts, x times negative 7 would give you negative 7x. And that's what we have in each box. Since I have the same thing twice, I double it. And it becomes negative 14x. That's our pattern that we see develop when we have the perfect square trinomials. Okay, that's why our equation here shows it's a squared, so that's just the part at the beginning times itself. The b squared goes at the end. And then this 2ab is because I have two of the exact same terms. It's a times b. In other words, a times b, that gives us ab. And the same thing happening here. A times b gives us ab. And since ab plus itself is 2ab, we're always going to get that pattern. It's 2 times whatever we have up here in our binomial. So let's look at seeing if we can kind of do this without using the box method. Can we recognize that pattern that we just discussed? Well, I know that it's going to be x squared at the beginning because I'm thinking about the box method, that area model. I also know I'm going to have, some middle term and then something at the end. And because I have a 5 here at the end of my binomial, I know it's like, well, 5 times 5 is 25. That's going to be the number at the end. But how do I get this term in here? Remember, if we take these two terms, x and 5, multiply them together, that's going to give me 5x. That's what would be in each of the like terms boxes. Okay, so if I were to have my area model here, 5x would be in each box. And since I'd have two of them, I could take 2 times 5x, which would give me 10x there. So x plus 5 times x plus 5 is x squared plus 10x plus 25. So now what we really want to do, today's lesson is on factoring a perfect square trinomial. So we have to start with this trinomial. And can we recognize what this would factor into? If we think about our area model, we know that we would have x squared in the first box, 64 in the last box, and we'd have to try to figure out what factors would give me the right combinations so that these two boxes add up to 16x. And maybe you even notice that, well, x squared is a perfect square. It's x times x. 64 is also a perfect square. It's 8 times 8. And look what happens when we check the rest of our area here. In each of these other two empty boxes, I'd be taking 8 times x. So I get 8x in one box. I get another 8x in the other box for a combined total of 16x. So I have my pattern here that develops. It's going to be x plus 8 times x plus 8. But really, since I have something times itself, one binomial times another binomial that's the exact same, I can really write this as x plus 8 quantity squared, because anything multiplied by itself is squared. and look at that relationship between the 8 and our answer here, our binomial factor, and the 16 and the 64. Okay, when we take that 8 and double it, we get 16. But when we take the 8 and square it, 8 times 8, we get 64. That's the pattern that we're looking at today. That's our special factoring. So here's number 5. The only difference on number 5 is that we have subtraction on the second term. X squared minus 20x plus 100. So if we think about our area model, we know it's x squared in the first box and 100 in the last box. So we can factor out x times x. We know it's 10 times 10 as a starting point at least. That would give us 10x and 10x, which adds up to 20x. The only problem is I need it to be negative 20x. Can you think about how we could make that negative 20x instead? Well, maybe you noticed if those were both negatives, that would give us negative 20x, which it does. It also still works to get positive 100 in the last box because a negative 10 times a negative 10 is a positive 100. So that's still fine. So factoring this perfect square trinomial gives me x minus 10 as the length, but also as the width. So I can write it as x minus 10 in parentheses squared. That's how we factor that perfect square trinomial. Again, look at that number. We had 10 was the value inside my binomial factor. If I double that, I get 20. If I square it, I get 100. All right, so you try this one. X squared plus 18x plus 81. Press play when you're ready. Did you recognize those two numbers and how they relate to a specific value? I recognize that when I take 9 and double it, I get 18. And when I take 9 and I square it, 9 times 9 is 81. If I'm ever curious or wondering if this is right, I can always double check my answer. If I take x plus 9 times x plus 9, I'd get x squared. I get 9x, I get another 9x, and then finally 9 times 9 is 81. So I get exactly what I started with. X squared plus 18x plus 81 is when I multiplied x plus 9 times itself. So x plus 9 quantity squared is the correct factoring. All right, so these next couple slides are really just kind of filling out like some area model puzzles, just showing that relationship using perfect squares. Okay, so when I say perfect squares, we're really talking about length times width to create a full perfect square, but that's also going to create a couple of perfect squares in the upper left-hand corner of the area model and the lower right-hand corner of the area model. So here we see that we have minus 9 in the parentheses, and when I double that, because negative 9 plus negative 9, I get negative 18. But also, when I multiply negative 9 times negative 9, I get positive 81. So here we're going to complete the area model, and we're going to write that math sentence at the end, kind of showing what the perfect square trinomial is and what it looks like as a factoring. So I already know my first box here is x squared, so that's x times x to give me x squared. And then if I think about what number has to go at the top, so something times x that equals 5x, well, that's just got to be a 5. So I do the same thing down the side, 5 times x equals 5x here. And now I have enough to fill out the last box. It's 5 times 5, which is 25. So I'm going to start by writing my perfect square trinomial. So I had x squared plus, well, 5x and 5x is 10x, and then plus 25. And I recognize that that was the result of multiplying x plus 5 times itself. So I can write x plus 5 in parentheses squared. All right, here's another one that's partially filled out for us. We already have the x times x is x squared. If I move down to this box and I think about, well, how did I get 4x there? I see the x up above, and then that means the number on the side must have been 4. 4 times x is 4x. then knowing I have a 16 over here, well, it has to be 4 times 4 since my number on the left is a 4. My number on the top has to also be 4. 4 times 4 is 16. And that's going to make this 4x. So I have a total area of x squared plus 8x plus 16. And that's the result of multiplying my length of x plus 4 times the width of x plus 4. So I write it as x plus 4 quantity squared. And I notice that 4 is a very important number here. When I double it, I get 8. When I square it, I get 16. All right, in this one, we have, again, part of it filled out, and quite a bit missing. Starting in the upper left-hand corner, I have x squared, so that has to be my x times x. In the lower right-hand corner, I got a 9, and it looks like I have a negative 3 on one side, so up here it's got to be another negative 3. A negative times a negative is how I get a positive 9 in that last box. So now I can do a few multiplications to fill out the rest of this. Negative 3 times x in both cases. So I get an area of x squared. When I combine these together is minus 6x and positive 9. And that was the result of taking x minus 3 multiplied by itself. It was the same length and width.